Yeah, we have a review coming out also in another Nature journal as well next month.
Wow.
Later this year.
Great to hear.
But I mean, it's just like good timing on everything, I guess.
Mm-hmm.
Great.
So in your CV, I noticed that you worked with Jungpyo at Princeton.
Yes,
Jungpyo,
I am working with him currently. We have like a very long project that is not done yet.
I see. I knew him from his undergraduate at Urbana-Champaign, so so I was surprised to
I'll
see.
Say hi.
Yeah,
I see him on Monday for.
Yeah, I see.
Yeah.
So you have a lot of Korean friends.
Yeah, I guess it worked out that way.
Am I the first one?
Yes, I mean, you're the first one.
Right.
Let's see.
Great.
Who else is here? Oh, Brian's here.
Oh, hi, Ben.
I guess anyone can come to this. I always
I actually signed up.
Yeah.
I actually signed up. I think Jeffrey gave a talk a few months ago. Here.
Oh, for this center? Yeah.
Yep. And then since then I signed up for it.
Oh, okay.
Yeah.
Let me. Oh, let's try to get the Wait, can I share my screen?
Yeah.
Yeah. Let me try to get that set up.
Yep.
Let's see. This. Wait, I have to do it again. Is this working?
Yeah, perfect.
Oh, okay, cool. Okay, cool. We can keep talking.
I'm sorry.
Yeah, so this is my first like nighttime seminar. So disjointed.
Yeah. By the way, it's also a little bit pain for the people in Korea too, because it's 10 a.m. but it's kind of like morning, so and I'm not kind of like morning type person. So
no, I mean I know the feeling. I don't think I've taken a meeting before 11 a.m. during the whole pandemic.
By the way, when I communicate with you through email, I find you don't get sleep even in like early midnight, like 1 a.m., 2 a.m., something like that.
Yeah, I work like I get really distracted, so I work like 2 shifts. Like I'll work from like noon to 6, and then I'll like work it out, and usually it's like Zoom meetings and people here. So and then at like 10 or 11, p.m. I'll read the archive at like 9, and then I'll work till like 4 or 5 in the morning and then start.
Wow.
But because no one bothers you, so like that's like I did most of the writing for this like that night shifts. Because I think it started because I was like when we were doing the project, I would have to hand off like this one in the CDW wild stuff.
Right.
We had people in like China and Europe, and so it was just for morning people. It was just really easier to like hand off something for them to read, and then you can sleep and you wake up and it's done, so you can go faster by working like a team.
I see.
It kind of stuck. But yeah, I'm okay with people like I sympathize if you don't want to wake up for this. You can watch the recording.
I see. That's cool. But I was worried about about your health, but it looks like
I mean people say I know I'm fine. I'm a night person. I work out a lot. It's fine. And
then I recognize that you are the national ranked fence athlete.
Right. I was on the U.S. national team for fencing when I was in college. I was the captain of the Penn team. Korea is much better than the U.S. Well, in my event. I mean the guy won gold medal in like I think it was 2016.
Wow, I see.
Yeah,
I didn't know that. So for you, let me say a few words. So some people listen to your talks through YouTube too. So they may not they cannot ask questions, but there could be some questions from the people listening to your talks through Zoom. And
is there a live stream on YouTube?
Yes.
Oh, okay. I see.
Yeah.
Okay.
So and then So let me slowly start. People may get come in a little bit later, but I can perhaps start by introducing you to the audience. So let's slowly start. So today we are going to listen to Dr. Ben Wieder. Is it right pronunciation?
Yeah, Wieder. That's right.
Okay, Ben Wieder.
Don't worry about it.
Okay, so he has been quite prolific for the several last years, and so he is probably very famous about his research. But so perhaps I don't need to say too much words, but I think I can briefly introduce his career to you. So actually, he wrote a few words about him for me. Let me read it, and then I would like to add a few words on top of that. So, so Ben received his bachelor degree from UPenn, and then surprisingly, he was also Roy and Diana Vagelos Scholar in molecular life science, and then he got the PhD under Charles Kane at UPenn. And then during the PhD time, he wrote several important papers about the Dirac semi-metal. And then he moved to Princeton, working with Jaid Hassan and Andrei Bernevik, and he published a number of the high impact factor journals and important theory papers. And then, as far as I know, he moved to MIT very recently. And then more impressively, I think I should highlight that he is also the national ranked fence athlete in US, and so I guess he's as healthy as in terms of his physics. So today, I guess we are going to listen to his recent work on the magnetic topological quantum chemistry. So Ben, you can start.
Okay, great. Thank you very much for the introduction, Gil, and thank you for inviting me. So this work, as we were talking about before, is the culmination of about 4 years of research from our team. And so I would like to introduce my team first before I get into it. So on the Princeton side, this work was done with Zita Song as a postdoc coming from Chen Fang's group. Maya Vernieri from Spain, who's also at Princeton during some of the time for this. Nicolas Regnal from ENS in France, also at Princeton right now. And Andrei Bernevik, who is the PI for this work and related works on non-magnetic topological quantum chemistry. And our team is quite international, so we have some people overseas. So Yuanfeng Zhu is a postdoc at Max Planck. Luis Alcoro, who did all the coding for the group theory side of this project, deserves a huge shout out, and he's at Bilbao in Spain. Barry Bradlin is a good friend of mine and collaborator with myself, and Jungkook, who's here, and he's a professor at UIUC in Illinois. And the chemistry and material side of this project was done with Yulin Chen at Oxford and Claudia Felser at the Max Planck Institute. So myself was at Princeton, and now I'm in the process of moving to MIT for more postdoc research. Okay, so this talk is based on 2 papers that are finally out. The first one is a theory paper on the archive, and the second one is a paper using this theory for a high throughput discovery of magnetic electronic topological materials. And this one will appear in Nature, I think the 29th, sometime before the end of the month. So before I get too into it, these papers are quite long. So I chose one set of them, or set of the material and them to focus on for this talk. But maybe it's not your preferred direction. You have some other interests or questions. So if any time we're not running out of time, at least in the beginning of the talk, feel free to interrupt me and just ask a question in the middle instead of waiting until the end before I go too far off on a tangent that isn't addressing what you had in mind. Okay, so with all that established, this talk is structured as follows. So first, I'm going to talk very generally about symmetries in quantum mechanics and how it relates to symmetry groups and representations of those groups. Then I'm going to talk about the theory of topological quantum chemistry established by Professor Bradlin and the Bernevik group. And basically, I'm going to do a very simplified, brief version of it because the main focus of this talk is on how to try to take the earlier theory and adapt it to magnetic materials, which are a lot more complicated. We'll talk about how spin is sort of represented in these systems and what it has to do with the symmetries of magnetic crystals. And then use that lead into the sort of new machinery that we've established for magnetic topological quantum chemistry and how that allowed us to theoretically discover new magnetic TI phases, which, time permitting, I'll talk about how we were able to predict some of them in at least a relatively large number of experimentally established magnetic structures. Okay, so to begin, symmetry very generally in condensed matter physics is the existence of an operation that either returns a Hamiltonian to itself when acting on a Hamiltonian, or returns a state to itself or to another state that is degenerate with that state. And if the symmetry operation is represented as say a unitary matrix in the basis of states, then if it returns a state to itself, it has an eigenvalue, which is here lambda. And in this talk, I wanted to focus on crystals, which have a little bit more restriction than just a general state psi. So crystals do not have continuous symmetries for the most part. I'm going to focus on at least 3D crystals. So I don't have continuous rotations, C infinity. I don't have continuous translations. So there's discrete rotations and discrete translations. And for our purposes, we'll take the crystal to be infinite and periodic in the bulk. And so this leads to the to Bloch's theorem. We have Bloch wave functions because of the infinite but discrete set of translations, which have a Fourier transform description in terms of crystal momenta. And so the set of symmetries for any particular system is described by a group in n dimensions. And so that group could be a space group if it's a 3-dimensional crystal, it could be a layer group if it's sort of a quasi 2D crystal that's embedded in 3D. These are sort of the most natural ones from real materials. And so on the right, there's some picture of some hourglass TCI, this KHB, HGSB, and there's a picture on the left of some depictions of the atoms in real space. On the right, the Brougham zone in momentum space for the momentum space. So to begin, the simplest example of a crystal is just a molecule. It's a 0-dimensional crystal. And so this will help us understand sort of how to think about how symmetries are represented in quantum mechanics. So basically, the group of your crystal is everything, including translations. And so for a molecule, there's no translation symmetries, but you still have symmetries like time reversal, rotations, mirror. And so the strength of spin-orbit interactions or spin-full interactions in the case of magnetism is represented in the square of the operations as they're represented. So, in a strong SOC molecule or crystal, time reversal square is to minus the identity. And you can think of lattice operations, on the macroscopic crystal, like twofold rotation, as dragging all the orbitals, like the s and p and d orbitals around. But because of coupling, that also drags the spins around, and they pick up a geometric phase or a quantum mechanical phase. So twofold rotation squared to -1, perpendicular twofold rotations anti-commute, at least their matrix representatives do. And then additionally, if, for electronic systems, if you happen to have weak or negligible spin-orbit coupling, then you gain additional symmetries because you basically have SU2 spin invariance. So I have the sort of tilde symmetries, these spinless effective symmetries, where time reversal squares to +1, twofold rotations squared to +1, and the matrix representatives commute. But it's worth noting that these are additional symmetries. There's always some infinitesimal spin-orbit coupling and spinful interactions. So as we go forward to the magnetic groups, I'm going to focus on the case where there's always some spinful interactions and leave out for now these sort of spinless cases. And so for the example of this molecule, it's relatively straightforward to see some of the symmetries. You can tell that it's a triangle, so it has rotation by 120 degrees. And it has some mirror about the x direction, but a little more subtly, it also has a rotation by a C6 rotation, so 60-degree rotation combined with inversion. So the product of two symmetries, it does not have 6-fold rotation or inversion, but it has their product. And this idea of having products of two familiar symmetries will also show up in the magnetic groups. So in terms of any particular group, a space group, a layer group, and a point group, the way to characterize them is in terms of the representations of that group, and specifically the irreducible representations. And so the terminology is if a group contains only unitary symmetries, then you refer to the representations as the irreducible representations. And if a group contains some anti-unitary symmetries, then you refer to the irreducible representations as the irreducible co-representations. And whether or not there's any pairing, you still call things co-reps if they have anti-unitary symmetries and things irreps if they're just unitary. Now, the reason that they are called co-reps is because the characters, which is basically the trace of the matrix representative, which in less group theory terms, it's the number of simultaneously valid symmetry eigenvalues for like commuting operations. The what's it called? The characters are the traces of the matrix representative, and so therefore that only applies to unitary symmetries because anti-unitary matrices don't have well-defined traces. So for both of these groups on the left and the right, you have the same set of symmetries, but they're different groups because they have this element of time reversal on the right that's not included on the left. And so this causes two of the irreps, the 1e and 2e irreps with complex C4 eigenvalues to be compared into a co-rep of 1e, 2e. And so the key ingredient is that there's this correspondence between states in quantum mechanics and irreps. So for example, for a molecule, the molecular orbitals transform in irreps or co-reps of time reversal or magnetic symmetries of the point group. So here, the 2e representation irrep on the left corresponds to a px plus ipy orbital on the right, which you can pick up from the phases of the wave function. And in the time reversal symmetric group, the px plus ipy magnetic atomic orbital is not time reversal symmetric, but the direct sum of a px and apy orbital, a two-dimensional co-representation corresponding to a doubly degenerate state, is an eigenstate of all of these symmetries. So in this sense, there's pairing. The co-rep on the right corresponds to the sum of two orbitals in this molecular orbital diagram. Right. So in 3D systems, which is what we're going to focus on, the symmetries, as long as they're embedded in 3D and not some strange sort of supersymmetry group, are contained within the in non-magnetic crystals, the 230 non-magnetic space groups. In a larger space of what are called Shubnikov groups, these 230 space groups represent only a small fraction. So for any 3D crystal, with or without magnetism being specifically lattice commensurate, so you do have translation symmetry, there are 1,651 groups that can contain the symmetries of the crystal.
Ben,
yeah.
Some people asked if you can use the pointer.
What is the pointer?
They mean the if you point where you are
like
explaining. Yeah. That will.
You can see my mouse.
Yes.
Oh,
yeah.
Good. Okay, sorry.
Yeah,
yes, I will use
fine.
the pointer. Okay.
Yes.
Sorry.
No.
Okay.
Thank you very much.
No. Please. No, this is good.
Yeah.
Okay. So the 230 space groups are a subset of the 1651 Shubnikov groups, and there is this whole other subset that we'll get to, a much larger subset of magnetic space groups. And so just as a brief pause, it is important to note that in the terminology that the build-out server uses and that we like to use, these are not all magnetic space groups. These, the 1, 3, and 4 types, which I'll establish the definitions of later, are the only magnetic space groups, because otherwise you have to call these type 2 groups non-magnetic magnetic space groups. And so we want to avoid that just by saying these ones are the non-magnetic, the regular space groups, and there's only 3 kinds of magnetic space groups. Okay. So as an example of a non-magnetic space group, consider this one. So I'll walk through what the terminology means. So the type 2 group, this means non-magnetic. This number is Belov BNS notation. Belov, Naranova, Smirnova, I forget which one it is, notation. So this numbering is established in this old Russian paper and used on the PCS. And this symbol, you can pick up the first 4 from Wikipedia, and this 1 prime, the primes tell you about how time reversal acts. So this tells you that you have the unitary group, PMMM, P being orthorhombic, MMM meaning it has MX, MY, and MZ symmetries, which is the product of these 3 operations. And the 1 prime means that you have time reversal with no translation. And it's important to know that the space group is an infinite group. So because it contains all the translations, and it contains this translation squared. So this notation is you act on your system with this operation, E being the identity, followed by some translation in the reduced units of the primitive lattice translations. So I have E200, for example, that's also a symmetry. But I also have symmetries like time reversal times translation and time reversal times mirror. Those are within the group. I just don't focus on them because you can always reduce them back to something like time reversal times nothing. So when we get to magnetic groups, the only difference is that I just won't have time reversal times nothing anymore. But it's always important to note that because the group's infinite, it's not like these symmetries are these time reversal times translation are unique to magnetic space groups. They just aren't traditionally listed as generators of these groups, of non-magnetic groups. And so on the right, I show an example of there's a crystal that is less invariant under the symmetries of this space group. And also there's a link to our website, topologicalquantumchemistry.com, where we have a very large materials database of all the bands. And so we're going to have an update for this coming out in the next month or two with all of the ICSD and all of the bands and fragile bands and all that neat stuff. So it's a shameless plug for a different paper that will be released in the next month or two. Okay, so in a crystalline solid, basically, you can focus on sort of one degree of freedom, electronic or vibrational phonons or magnons. And you can just ask, can I describe the system fairly or unfairly in some approximation in which mean field theory is valid? And that allows you to establish a quadratic Hamiltonian whose eigenstates form bands in momentum space. And so those bands at each K point are, the eigenstates are called block states. And they form, this structure that if it's nice, it has some clean features at the Fermi energy. Maybe this one is the direct semi-metal with a crossing along this line gamma Z. But a typical band structure is just this mess, and people sometimes say it looks like spaghetti. And so the degeneracies in these pictures are described by two things. They're described by local topology, like a Weil point, where you can surround the object with some sphere or some loop that has some non-trivial topological invariant that doesn't rely on any symmetry other than translation. Or I can label the states with symmetry eigenvalues and ask whether the states have distinct labels, and that allows the states to cross without a gap opening. And so the labels are what we're going to focus on for most of this talk because they're the simplest part of the story. And so they are these small co-representations of the little groups. And maybe I do more. Yeah, okay. And we'll get to what that means in a second. But for our purposes, when you look at a band structure in some paper, you see some labels, gamma bar plus, gamma 6, and that refers to the symmetry eigenvalues and the matrix representative of the symmetries at that point. And you can use these to create all sorts of interesting theories. You can talk about phase transitions, CDWs, like magnetic phase transitions, and you can also infer topology from the various combinations of the co-reps that the occupied bands transform in. And so formally, the little group is the group of all the symmetries that leave a K point invariant. And because translations act trivially on K, they act as a phase in momentum space, then the little group is an infinite group. But you can come up with a finite set of representations that contain all of the sort of unique symmetry eigenvalues that characterize the group, basically everything modular translations, by focusing on what are called the small representations, or the irreducible small representations. And so what this course comes down to is if I have some band structure and I write some type binding model, I want to label the states in the type binding model by some co-representations of the little groups, and that'll tell me something about, for example, what the degeneracy is supposed to be. Do I need to add extra terms? Or maybe there's something about the topology, or whether I can't smoothly connect all these states and make it some more trivial kind of insulator. And so to do this, I need to know all the different little groups and all their small co-representations. And that's sort of a non-trivial task. For the non-magnetic space groups, that's been done already. So a old resource that at Penn we used a lot going into the end of my PhD and the beginning of my postdoc was this book by Bradley and Cracknell, Mathematical Symmetry of Solids. And this contains all of the little groups and tells you their coreps, and their small coreps in terms of the irreps that are known as the abstract point groups. So these are point group-like objects that have sort of the funny squares from symmetries that are like glides and screws that don't act quite like a point group. And so, you could look at, say, the R point, and you could say, okay, it's abstract finite group G14 extended by central extension by T2, and then I have to look at the irrep2 and irrep4, but they're paired because the 3 in this table means, I think, the double groups is you pair them. So it's not great, but it's tractable. You can do it as a grad student. You can pick it up. And then more recently, for topological quantum chemistry, Luis Alcoro translated this and rederived it all into an accessible tool on the Bilbao server. You don't need to invoke the abstract finite groups. So I click on the same space group. I would click on the X point here. And I would just get a bunch of list of matrices and symmetry eigenvalues and labels. And that can be fed directly into the output of some DFT. They have tools for that. So I can, though probably in Cracknell is very nice, I can at least ignore the tables in it for now. And so this makes the process of using the small coreps a little bit more manageable. And it was basically because of advances in websites and computing, and because the problem was fundamentally done 50 years ago. So the only thing new to do in this case was to just make the website. And so to show very briefly what you can do with small coreps, it's basically the game that a lot of people have played in the last few years is, how do I have some approximation of the electronic band topology in a material from basically a cheap calculation? So what happens is somebody takes a crystal, they think it's interesting for chemical purposes, they convince an X-ray crystallographer to measure the structure and report it. And if they get a relatively pristine sample, they can say that it has some space group, it has some atoms that live somewhere throughout the unit cell. And for our purposes, so you take the output from this, which is in some format, and you run DFT on it, and you get some bands. And the question is, if I just stare at a band structure, and I don't want to eat up lots of computer time, or I want to do this thousands or hundreds of thousands of times, how do I know which materials are topologically interesting? And so that means they have some quantized response, they have some interesting surface states, that kind of thing. So integrals are expensive. Wilson loops, Berry phase, that's bad. We don't want to do that. Surface Green's functions are, custom calculations, also bad. So the question is, what is the absolute cheapest calculation you can do? And that more or less is you can get the symmetry eigenvalues of the wave functions for the unitary symmetries, all the high symmetry points, which then you can then, if it's a non-magnetic space group prior to our work, you can then decompose into the multiplicities of these small coreps. You say, okay, I have 3 occupied bands that are inversion odd, I have one that's inversion even, maybe I have some C4 eigenvalues, and maybe there's some, and so that at least is something I can work with that wasn't very computationally expensive to obtain. And so there's been this sort of tremendous number of works that focus on special cases, what those coreps mean in terms of topology and boundary states. And so basically the procedure is you take your band structure, you look for something interesting in the spectrum as it transforms in terms of coreps, and then you can sort of classify, you can grade it a little bit. And so the first class of things you'd find are topological semi-metals, which are gapless systems. They're systems that have a gap almost everywhere except at a collection of points. And so there's a tremendous variety of topological semi-metals with interesting boundary states. And so the coreps in these cases allow you to make a one-to-one link between the occupied bands at some high symmetry point and some K.P Hamiltonian. And then you can look at the topology of the K.P Hamiltonian for things like large Chern numbers or unusual topological phase transitions. And you can look for K.P Hamiltonians that don't have a correspondence in high energy physics and sort of decouple this early feeling that top topology and solid state materials was all about colliders in a lab, Dirac and Weyl particles, and make it more about it's just electronic bands, but that doesn't mean it's not interesting. There's still a lot of experimentally relevant effects that are beyond what you would get in solid state or in high energy theory by relaxing some Lorentz symmetries or having a larger space to work And so we found a tremendous number of these, and from the K.P. Hamiltonian, you can also figure out the boundary states. So you can have topological Fermi arcs, topological hinge arcs, and some more exotic bulk boundary correspondences. And if you don't have a semi-metal, and so maybe I have a gap everywhere, or I have some funny band structure that maybe it's not an insulator, but it's at least have a gap at all the high symmetry points. So you could ask, even with the coreps, what kind of insulator is it? Is it topologically interesting? And so one way to do that is to come up with some set of rules for all the things that are not topologically interesting. And so that's basically what elementary band representations are. So to take a return to group theory, the elementary band representations are sort of the generalization for space groups or groups of translations of the E-reps or the co-reps or the point groups. And so the simplest example that they always use in these TQC papers is some variant of the Schuster-Heger model of polyacetylene. And so here, the 1A and 1B Wyckoff positions are invariant under inversion symmetry. And the 2C position does not have inversion. So there's two sites that are related by inversion about 1A or about 1B modulo an integer lattice translation. And so you can place exponentially or better localized orbitals that respect the symmetries. So to make it a Wanné orbital, it has to be an inversion symmetric wave function of some kind on these various sites. And you could ask in some weakly coupled limit, if I look at the band structure, what are these symmetry eigenvalues? What are the coreps in momentum space, the small coreps that are induced by these 1A orbitals in position space? And so this kind of table over here gives you this correspondence where the up arrow is the induction between some site symmetry E-rep or co-rep, which is like a irreducible representation of a point group at the 1A or 1B position, and the symmetry eigenvalues in momentum space, which are like these small co-reps. And so this tells you the combinations of small co-reps that correspond to Wanné insulators, which are basically atomic insulators with exponentially or better localized Wanné functions. And so the deal is, in any dimension higher than 1, the kind of topology that we care about, without getting too much into the details, is something with spectral flow. So in some integral or some surface or boundary state, there's at least, at best, a 1D chiral mode or helical mode or a Dirac cone, or even in some very strange integral, in a Wilson loop, there's some winding for at least some subset of the bands. And so what you can do is you can take all theory of topological quantum chemistry is, you can enumerate all of the elementary band representations of all of the 230 non-magnetic space groups. That gives you all of the trivial insulators, and then you can construct these formulas, which are known as symmetry eigenvalue indicators or symmetry indicator formulas, of which an example is the Foucault formula, the parity criterion for a 3D topological insulator. You just ask, do your small coreps obtained from your cheap DFT calculation match any of these EBRs, or do they not match it? And if they don't match it, then since I know what all the trivial insulators are, then whatever I have is not trivial. And so, focusing on the two cases that you may have heard about, so this, briefly, fragile topology is this case where they don't match a positively valued linear combination, but maybe I cut an extra bands and sort of smooth that over and cancel it out. But there's also cases where I can never add an EBR, I can never add trivial bands, and I can to cancel out this fact that my coreps, the multiplicities, don't match any trivial insulator. So this is stable topology. And so stable topology is what corresponds through all these papers that have been established to topological boundary states with dimension greater than 1. So hinge modes, Dirac cones, fourfold Dirac cones, things like that. And so basically, after focusing on the major families of eigenvalue indicated topological insulators and crystalline insulators, we can say what the expected boundary states are just from figuring out the combinations of coreps in cases. There are of course many cases where you don't have these, you cannot have these eigenvalue indicators like non-centrosymmetric crystals or most non-centrosymmetric crystals, or at least, so specifically those without roto inversions. like S4, C4 times inversion symmetry. But in the cases in which you do have them, like say elemental bismuth, you can run this calculation and recognize that it's already some sort of exotic form of topological crystalline insulator before you've done any expensive calculation. So, if you just calculate the band structure of bismuth and look at the parity eigenvalues and compare them to the trivial insulators in the same space group as bismuth, you'll find that it doesn't match. And that gives you a hint that you should do some more expensive calculation, like construct a Taylor type binding model, a surface or a hinge Green's function, and then look for what is in what way does the non-trivial topology manifest. And so just to note, this also works in fragile topology, and you get in many cases 0D corner states, or in some models twisted boundary states, either in metamaterials or type binding models. But for the purposes of this talk and for magnetic topological quantum chemistry, we are focused on stable topology with the at least initial goal of predicting magnetic topological crystalline insulators that are stable to the addition of things like core shell atomic orbitals. Okay, so the first half of this talk, I've outlined how to date the theory of band structure as applies to topology has been used to discover a lot of materials and exotic phases, at least in the mean field. And so now the big question is, there are also magnetic crystals. In some cases, the theories of magnetic crystals in terms of the kinds of predicted topological phases are more interesting than the non-magnetic ones. And well, there's some linked topology and magnetic structural or order transitions. So you would like to be able to use the same machinery to predict some very interesting or complete sets of magnetic topological phases. And these include quantum anomalous Hall states and antiferromagnetic TIs. And I'm going to explain some of these. There's semi-metals. And as I'll get to in a few slides, are these very exotic insulators whose bulk topology behaves, or bulk low energy theory behaves kind of like Axon electrodynamics, this sort of exotic, modified form of electrodynamics. So you like to be able to play with that in a lab, especially in a setting in which you can play with the magnetic order and also affect transport properties as well. However, there are a significant number of issues. One, magnetic systems are correlated in most cases. So the question is, can I ever write down an electronic theory in the mean field that is in any way valid or meaningful? Is the magnetic order measured? So it's a little bit of a fraught exercise to predict theoretical magnetic ground states. That in itself is very difficult and sometimes controversial. So you'd like to restrict yourself to systems where they have identified the magnetic order through something like neutron diffraction and reported it in a way that you can use it, i.e. with the magnetic space group. And even if you have the magnetic order, it might not be lattice commensurate. I mean, it is at the end of the day some kind of spin wave, and there's no reason a priori that the spin wave has to exactly match the lattice. And so let's say, for the purposes of our study and the remainder of this talk, that all of that is still true. You can use mean field theory, you measure the magnetic order, and you have it to be lattice commensurate. If so, it's still not that easy. And one of the main reasons is there's just a whole lot of magnetic space groups, and they're very complicated. And so to give a brief overview of the magnetic space groups, there are three kinds. The first kind, type 1, do not have any anti-unitary symmetries. So they're just the space groups modded by time reversal about a site. The type 3 groups have some symmetries like a unitary symmetry H times time reversal, maybe with some fractional translation, but they like a glide times time reversal, maybe just a mirror times time reversal, but they don't have any symmetry, any of these, they don't have H or T individually. And the last kind, the type 4 groups, are the kind that has time reversal times a fractional lattice translation, but they do not have this translation or time reversal individually. And as we show in the paper, and as you can find in some of the older textbooks, all these groups are different kinds of subgroups of non-magnetic crystals or non-magnetic space groups, which makes some sense because there has to be some parent non-magnetic phase from which you've induced the magnetic order that transforms in this magnetic space group. And so in a lot of cases, like this crystal here, which transforms in a type 4 magnetic 1D group, the magnetic unit cell, where you have the actual translation symmetry, is larger than the non-magnetic cell, which would be the cell if I just turned off, however you want to call that, the blue and red spins. So in magnetic materials, the unit cell is also potentially very large for your DFT calculation because the periodicity of the spin wave is much larger than the lattice constant. So that is another complication. So, okay, now if you know all the magnetic space groups, that is sort of only the beginning of your problems. So there are many of them, and it's important to note that just because you know them doesn't mean the same thing as that the magnetic order, the phenomenological magnetic order, whether it's a ferromagnet or anti-ferromagnet or ferri magnet, isn't always in one-to-one correspondence with the magnetic space group. So there are many cases in the type 1 and type 3 groups where the same magnetic space group can correspond to two different magnetic orderings that you would classify as phenomenologically distinct. And additionally, it's important to note that if you just look at the spin waves, you might think that you have much higher symmetry with all these different spin rotations and directions that are broken. But and for the purposes of predicting band topology, you have to understand that whatever the spin space group is, it's strictly a subgroup of the non-magnetic group. So the spin wave is always subject to the sort of crystal field, which reduces the symmetry and the degrees of freedom to at best be whatever you had before you induced the spin wave. And so even if you work this out and you sort out the difference between the spin wave space group, the phenomenological magnetic order, and the magnetic space group, the magnetic small coreps, the collections of simultaneously valid unitary symmetry eigenvalues at all the K points, they don't exist. There's no textbook like Bradley and Cracknell prior to our studies that has the tables of the Irreps, the coreps of the magnetic small or little groups. And at best, there was this initial tabulation by Miller and Love at a large number of isometry points, but it was done in Fortran in the 60s with punch cards. And I mean, it's very hard, even in a good copy, to read what all these symbols are. There's only like 3 copies of this book in the world, and at best, you can kind of get a photocopy. So it's not something you can really check yourself against. So, we looked at the idea of paying someone to digitize this book or some way to sneak into the Harvard library and get it or something. But, at the end of the day, the only solution, because it turns out this book doesn't have everything, is to do it yourself. So so using an old book is out for getting the magnetic small coreps in a complete fashion. That actually lets you do a DFT calculation and then analyze the results. And even if you had them, you still have to run the machinery of topological quantum chemistry to calculate the magnetic elementary band representations. There's some subtleties that I did not discuss about sometimes not every atomic limit splits in a way that is a one-to-one correspondence. Sometimes you get 2 EVRs out of 1. So there's some additional checking that's a little bit on the edge cases that's a pain when it has to be automated over the hundreds and hundreds of magnetic groups. And lastly, even if you have all of these and you compute something, you don't know what to do with the symmetry eigenvalues because the magnetic eigenvalue indicators don't exist. So Ashton Vishwanathan's group did a very nice paper where they did some of these calculations as an intermediate step, so they did not report all the results in a publicly accessible fashion. But if you basically perform, some band structure combinatorics where you look for the linearly independent combinations of symmetry eigenvalues that are topologically non-trivial, you will get 2 things that come out of this calculation. You get the indicator group, like Z4 cross Z2 cubed, and then you get some collection of small coreps that correspond to some jumble of topological insulators and crystalline insulators and semi-metals, and you have to sort it out. And so at the level of this previous paper, they got the indicator groups, but they did not sort out the physical meaning of them. So you still have to, if you reproduce this calculation, figure out at the end of the day what all these numbers mean if you want to make some prediction about real materials. And so a long story short is that we did all of this. We sat down and we calculated all small coreps, and Luis made all the tools. We checked all of them with some independent calculations to make sure that the splitting makes sense and they have all the appropriate group algebra properties. We calculated all the magnetic elementary band representations, and we redid all the ones for the non-magnetic groups and placed everything into the same tool. And we calculated the complete set of eigenvalue indicators of magnetic topology for the fermionic system. So basically, if it's electrons and there's magnetism, as long as it's not orbital magnetism in a weak spin orbit crystal, so then there'll be some spin interaction of some kind, some DM interaction or something fancier, or it doesn't really have a proper name. And so for these kinds of crystals, you want to use the double groups, or these spinful groups. So we focused on those, and that in itself took up a tremendous amount of time and effort. So at the moment, we have not completed the same calculation for the sort of bosonic or spinless eigenvalue indicators, though it's partially complete. We may release it, and we have some time in the next couple of months. So give a real quick background, just to make sure. Right, okay. So the magnetic EBRs, the difference between them and the EBRs without magnetism is that they're induced from not just atomic orbitals, but magnetic atomic orbitals. So previously, when I talked about these px plus ipy orbitals, these don't show up. These are basically angular momentum states in some hydrogenic ion. And normally you just see px and py orbitals, like what you make the periodic table out of. But for the magnetic cases, you basically have to subject some molecule or some ion to the magnetic crystal field splitting in a symmetric manner of the sort of local magnetic environment. And so you're using sort of, in some cases, you're using familiar orbitals like dx, y, and s. In other cases, you're using the angular momentum eigenstates instead of the atomic orbitals, which are the things that have a one-to-one correspondence with the EREPs of the point group. So with the last bit of time, I'm going to talk about what you get from the eigenvalue indicators. And so basically what you do is you compare the complete set of magnetic elementary band representations to the coreps through some calculation along the Smith normal form of the multiplicities of the small coreps in the MEBRs. And then you ask, basically, if I invert bands, do I get some obstruction like a direct semi-metal, or can I still have a gap along all the high symmetry lines and planes? And that tells you how many groups admit some kind of structure where you can have symmetry indicated non-trivial topology. And you find that in the spinful groups, there's 800. So that's also not something you can do by brute force. And that would be the end of it. We wouldn't be able to do this project if there was no way to simplify it. But it turns out that in some cases, there's a one-to-one correspondence between some high symmetry group and the topological band, some low symmetry group. So like in a case where I have inversion and mirror, maybe I can forget about the mirrors, and it turns out that all the bands that were labeled as topological remain labeled as topological in the lower symmetry group with the same labels. And so in that case, there's a one-to-one correspondence, and whatever's going on in the high symmetry mirror symmetric group, I can worry about it later as some edge, special case of just the inversion symmetric group. So once we eliminate dependencies, there's only 34 magnetic and non-magnetic space groups that have some eigenvalue indicator structure that is not fully dependent on a lower symmetry group. And this is something you can do by brute force. And so, in these groups, with a lot of trial and error and guess and check based on basically the formulas for Axon insulators and Chern insulators that were established, we were able to get all of the eigenvalue indicators in the minimal groups and then show how to use them in the non-minimal groups. And so what we did was zeta sum for the insulating phases that permit them constructed layer constructions from which you could basically read off the boundary states in bulk topology. And by combining that with the known eigenvalue indicators, like the Fang-Gilbert-Berndevic formula for the Chern number, you could figure out which states are quantum anomalous Hall and Axon insulators. And uniquely, some of these are semi-metals. So for example, on the right, you can have this case where this would be picked up as a topological band because there's no crossings along high symmetry lines and planes. But the eigenvalue formula from, say, Chi Wu Zhang says that there's an odd Chern number here and an even Chern number here. So the descent relation tells you that there is an odd number of Weil points in the middle somewhere. So this is a symmetry indicated a Weil semi-metal. So we call this a Smith index Weil semi-metal in the paper. Some of the things we found are new classes of magnetic TIs and TCIs. So to briefly review, the sort of very famous established classes of magnetic TIs are quantum anomalous Hall states and Axon insulators. So quantum anomalous Hall states are like a Chern insulator in every KZ slice in some direction. So they're basically decomposable into a stack of 2D Chern insulators. So And an example is like the Haldane model, where you can take a TI and make it very flat and have it some spontaneous magnetization. And there's many studies of these over the years. So I apologize if anyone watching is not cited. And so these have been realized in experiment. And also, most recently, people have begun to focus on what are known as Axon insulators, which are insulators whose bulk response theory at low energies behaves as if you're in a medium that has axions. So if you insert an electron, it's subject to the Witten effect. It's basically you bind a magnetic monopole or vice versa. And these have some topological magnetoelectric effect if appropriately configured. If you glue Chern insulators to cancel out some additional boundary states. They have some quantized Faraday and Kerr rotation. No, I didn't write down Liang's paper. I apologize. And so they've been the subject of a lot of focus recently for two reasons. So one, they've been recognized to be some form of what is known as a high order topological insulator, which is sort of a class of topological crystalline insulator where none or some of the boundaries are gapped, but domain walls in symmetrically constructed models between gapped boundaries have some gapless mode in 2 fewer dimensions or more than the bulk. And so, for example, if you take an inversion symmetric PI and you gap out all the Dirac cones in a way that preserves inversion symmetry, then you're left with this odd number of chiral modes, here 1 chiral mode that traverses your sample. And so, on the right, you would call this a magnetic Axon insulator. On the left, you'd call it a 3D TI. But all of the paper, they both have a bulk response theory that's like theta equals pi in E dot B kind of axion theory. And they both, because of that, have an odd number of massive or massless Dirac cones on the surface, leading to a half quantized Hall conductivity. So, that's a very universal picture, and I'm not focusing on whether it's 4-fold rotor inversion or time reversal. So all of these are axionic TIs or topological crystalline insulators. And the second reason that people care is because you can finally make them in experiment. So this group, Ochulkov and Otrokov, in this, I didn't write the formula, this Mn2-BITE4 family, they are recognized to be some form of axion insulators. So finally, we have these sort of intrinsically magnetic axion insulators to play with. It'd be great if we had more of them. So in terms of the eigenvalue indicators and layer constructions, to give an example of how the familiar phases work.
Ben, can I ask a question? So in the previous slide, so long time ago, there was a proposal about the anti-ferromagnetic topological insulator by Roger Meng and Joel Moore.
Yes.
I thought it's different from the Axon insulator, but you are saying they are almost the same or the same. So are they the same phase or?
So I would say that so in the paper we talk about this, and when you run the Smith normal form calculation, none of the type 4 groups, those with the AFM time reversal times of translation, are minimal groups. They all have their topology induced from a lower symmetry group. So that tells you, at least in terms of eigenvalue indicators, which they have in the paper for the inversion symmetric case, whatever's going on with time reversal times translation is not the sort of most fundamental or minimal ingredient.
Good.
And so, for example, in their symmetry indicated case, where I look in one of the BZ planes and look at the sort of Foucault formula, I can forget time reversal times translation and just keep the parity eigenvalues, and and theta remains quantized to pi.
I see.
So
I see.
Maybe in the other, I can quantize theta to be pi with time reversal times translation, but it won't be symmetry indicated. But if it is symmetry indicated, I never even have to tell you about the AFM part.
I see. Good. Yeah. Thank you.
Yep.
Yeah. And I have another question. So you said you classified almost all the topological band insulators in the magnetic space groups with the mean field magnetisms, I guess. Do you know what's going to happen if I have defects in the magnetic orders? Like a domain
so it
verse or
so if the what's it called? So if the defect is sort of like smooth and you can think of it as like a mass defect, and if the magnetic order is like a spin density wave, then we can talk about like, does it bind? This is sort of like the CW physics that we're doing, where it's some mass vortex and it's chiral modes or half quantum Hall layers or stuff like that. And if it's like a, you know, like a screw dislocation or something, then there's some established, you know, literature by like Shalon Shi and stuff about like the kinds of chiral modes you'll find.
Right.
Or,
Yeah.
So we're working on it. We have a paper on defects and higher order TIs and some of these new phases coming out.
I see. Okay.
But it's in those two limits. It's like a, you know, commensurate, you know, lattice dislocation, or it's a very smooth mass defect kind of thing. But I don't think it's any more exotic than a non-magnetic case.
I see. Okay, good. Yeah.
Give me 1 second. I'm gonna turn the air conditioner on. It's just really hot in here.
Okay.
But like 30 seconds.
Yeah. Yeah.
All right. All right, thank you. Sorry.
Yep.
So.
Yep. You can go on.
Right.
Yeah. Thanks.
Okay, good. All right. So to give an example of what kinds of constructions you would do for these eigenvalue indicators, I'm going to focus on the absolute simplest magnetic space group with a non-trivial indicator group. So the simplest example is magnetic space group 2.4, which is generated just by inversion and translation. So this is like, for those of you familiar with space group 2, forgetting the time reversal. And so the symmetry indicator group that is returned by the calculation is Z4 cross Z2 cubed. And by, you know, some creative guesswork, you can figure out that the Z4 number is the strong Axon insulator invariant, and the Z2 numbers are the Chern numbers in basically the weak Chern numbers in the Brillouin zone boundary planes in K-space. And it's worth noting that the odd values of the Z4 invariant correspond to Val Semi-Metals, as I showed on this slide on the right. So focusing on the even cases, you can write down, for example, you can layer construct in real space a quantum anomalous Hall state by just placing a Chern layer in a way that's pinned by inversion symmetry in one of the unit cells, tessellate space with it. And you can figure out what that corresponds to in terms of eigenvalues in momentum space. So here, that's a, you know, we can say that it's like having band inversion at this inversion invariant point and this inversion invariant point. Or I can stack this with another oppositely signed Chern insulator with a half translation separating it, and I can construct an Axon insulator where these alternating Chern layers sort of have some alternating chiral modes in the boundary that you could imagine hybridize into the chiral helical mode of an Axon insulator. But it's also worth noting that if I had made this red Chern insulator blue, I could construct a non-symmetry indicated quantum anomalous Hall state that has the same 2, 0, 0. So, and a Chern number, say 2 per unit cell. So the indicators are not the end of the story. They're the beginning, and you have to do some calculation like surface states or Wilson loops, and even just look for the gap for wild points to make absolutely sure, especially in these magnetic cases. But, so to conclude, this is not the end of the story. There are new phases that show up that are closely related to the recently discovered high order topological phases in bismuth and MOTE2. So for example, if I look in a magnetic space group with only mirrors, PMMM, I find that it has some Z4 index, but for doubled states that come from basically the anti-commuting matrix representatives of spinful mirrors. And so this is a Z4 invariant, and I can, without closing a gap or breaking a symmetry, I can add time reversal, and I can go up to a space group, what you would call space group 47, PMMM1 prime, so this time reversal. And this has a Z4, and this Z4 refers to a high order topological phase that has some mirror Chern number 2. But then I could go down again to something with just C2 in time reversal or just inversion time reversal, and keep the sort of hinge modes or surface Dirac cones that are indicated by the Z4, or in this case, not indicated by the boundary states or a Wilson loop. And so the statement is, okay, yes, this thing on the right is some kind of TCI, but you can smoothly connect it in parameter space to what you would call a high order TI. So the distinction between mirror TCI and rotation anomaly TCI and high order TI is a little bit, too fine grained. And so a bigger picture, these are phases of matter that have 2 plus 4n massive or massless Dirac cones on any particular surface that you look at. And in some boundaries between them, appropriately symmetrized, you'll have helical modes that are anomalous. And so just to show how this works, in this mirror-only group, the indicator group is again Z4 cross Z2 cubed. And the eigenvalue indicators have the same form as in the lower symmetry group with just inversion. But here the coefficients are halved because every state's at the high, all the states at the high symmetry points come in pairs. And so you're looking at pairs of states. And so these are the eigenvalues for this, what you would call this high order topological phase, this D2H high order TCI. You can layer construct it from just regularly spaced mirror churn insulators with odd mirror churn numbers. And so in this case, the stacking direction is like the X direction, and the whole sample has one mirror protected helical mode that goes around that, depending on the way in which you embed the symmetries or restore them, is the same as a hinge mode in a high order TI. And the thing about these phases is they're not Axon insulators. They're magnetic, but they have trivial theta angles. And so there's this question of if they have any quantized response at all. So how do I think of them in a low energy theory? And this is a significant open question. We have some theoretical works on it that will be coming out very soon that I hope will provide clarity on it. So this is a little bit of advertisement to keep a lookout for some interesting directions in experimentally measurable response effects beyond axion electrodynamics in topological crystalline insulators. So this is sort of my last main slide, though we have a bonus slide at the end if we want to. And so basically what we did, I'm not a DFT guy, so I'm going to just tell the DFT story really short. So we established all of the meaning of all the, the ingredients for magnetic topological quantum chemistry and symmetry-based indicators. And so on the Bilbao server, we have a repository of initially around 700 magnetic structures that are experimentally confirmed through neutron diffraction experiments. Now it's over 1,000. There was 400 of them that were lattice commensurate and where we could run DFT with some values of the Hubbard U or fancy functionals and get a convergent band structure or a convergent energetics leading to a band structure. And if we run the magnetic TQC and the SIs, we find 130 magnetic TIs and semi-metals. So many of these were not known previously. And so a great example is this NPBI, which is an Axon insulator that has a huge gap if you look in the experiment or in the DFT. And then we also find some higher order semi-metals and semi-metals with large Fermi arcs. So if you're interested, there's a very large list of material candidates and a lot of details in the archive paper. And an update will be coming out in about 2 weeks when it gets published in Nature. So to conclude, there are some future directions that you can go with this. And I'm going to focus on 3 of them here. One is on the idea of a very field theory idea of symmetry enhanced fermion doubling. So in the talk, I didn't talk about it very much, though there is a bonus slide if we get there, where the boundary of some topological phase or some topological crystalline insulator is sort of half of a lattice regularized semi-metal. So in the case of like an Axon insulator, I have this very nice picture from say Chi-Hugh Zhang of I have a bulk that has some non-trivial theta term, and I have, let's say I have a vacuum that has a trivial theta, and the boundary has some half quantum Hall that if I have some axion odd symmetries has an odd number of massless Dirac cones that looks like half of a semi-metal that you would be able to lattice regularize in 2D. So in a sense, the boundary circumvents the parity anomaly. So that picture is very neat, but for fancier topological crystalline insulator phases, like these magnetic non-axionic TCIs, we don't have the high energy theory, or we haven't figured out which one corresponds to this phase. So we don't have this neat picture. And this neat picture sort of unlocks, the ability to go from these, very constrained higher order TI models to this, very general axion electrodynamics picture that lets you predict sort of robust experiments with defects and disorder in real materials. A second direction is what the spinless SIs mean. So if I induce orbital magnetism in weak spin orbit crystals, what kind of TCI phases are there? So we know that there's churn insulators, orbital churn insulators, orbital axion insulators, but is there anything else that's interesting and symmetry indicated? That's an open question. And lastly, something that I'm beginning to look at in my new research is there anything you could say about quantum spin liquids from the perspective of magnetic topological quantum chemistry? So translating this very field theory and anomaly focused language of quantum spin liquids and Ising system to this language, topological quantum chemistry, would open up things like large databases of spin liquid materials, which would be very useful for all sorts of interesting experiments. So that is all the main body of my talk, minus the bonus slides. So I think that's a good place to open up for questions. So thank you.
Yep. Thank you for the beautiful talk. So the session is open for the questions. So if anyone has question or comment, it's a good time to speak up.
May I have a question?
Hey, Uncle. Yeah, sure.
Do you have a material candidate for the helical hyoid TI that you newly found?
No.
No,
there was one that was maybe mentioned in the first archive draft, but it was a mistake. It didn't work. Well, so it's an open question.
Or do you have any strategy
Yeah, I mean, the biggest issue is you need a mirror symmetry, and it's just like you need a lot of mirrors, and so you just have to have a lot of magnetic moments. Can't be fixed to a mirror plane, so they have to be magnetic moments all over the unit cell. So if you can induce magnetism in a, you need to start with mirror. So if you focus on, the short answer is, you can focus on something like bismuth and induce the right kind of magnetism, for example. The longer answer is, if we can wait a little bit. So for Axon insulators, you don't need all the symmetries that symmetry indicate, as we talked about with the earlier paper with the antiferromagnetic TIs. You can still use a symmetry that has no eigenvalues, like time reversal times translation, and pin the axion angle. So when we figure out how many of these indicating symmetries can be broken while not breaking the bulk topology, then we'll really be able to tell you what is the simplest magnetic order and where to target to find these phases. It just might be beyond symmetry indicators. So the short answer is, guess and check, but the long answer is, maybe 2 years we can do better.
Okay. So I have another question. So other than the helical hyoid TI that you introduced, did you find any interesting new topological phase from your symmetry indicator?
Nothing you didn't know about.
I see. So how is that? Why you shouldn't? Well, you have a complete search for the symmetry indications, but how could we couldn't find? How could we find all magnetic topological phases without the sophisticated method that you've developed?
Well, so you could do what Zeta Song did, and you could try to make all the elementary layer constructions in all of the magnetic space groups, and that would give you a huge subset of all the gap phases and all the boundary states of those phases. So you could do what he did in his Nature Communications paper for all the magnetic space groups and see if, because that gives you things like the glide TCI that we found that is not eigenvalue indicated. So you'd be able to read that off from the layer constructions. You could also try to do some very creative Wilson loop and nested Wilson loop arguments, like sort of a couple of the Andre people have done in our paper as well. And if you have some particular intuition about, you could pick out one family at a time until you're convinced that you've got everything or close to everything. But people did a good job. And the reason this worked so well is because a lot of smart people had a lot of good intuition about what the magnetic topological phases should be. So some of it was already figured out, and we were able to build upon that. So we weren't working, completely blind.
I see. Thank you.
Can I ask you a question?
Yep, go on.
So in your previous slide, you showed that you found a magnetic Dirac semi-metal mangan germanium oxide.
Yeah.
But I saw this paper, and I saw that this system has a trivial geometry indicator. So I wonder, how did you find it? This material?
Was it trivial, or was it not defined because it's like a enforced semi-metal or something? Some of these are some of these are not defined because it's still a topological semi-metal then.
Yeah, for this material, I remember that this has only the combined PT symmetry plus C3 rotation symmetries. So yeah, in such materials without any information on the symmetry indicator, how can you find real materials in the database?
So you can't find insulators, but you can find semi-metals when you know that the eigenvalues lay along a C3 invariant line don't match. So like topological quantum chemistry has this ES and ESFD class where they're eigenvalue indicated, but they're, it's just a fancy way of saying band inverted semi-metal. So if I look at the occupied bands, I would say that I cannot form an insulator, like forget trivial insulator in this case, because C3, if the C3 eigenvalues are different along the high symmetry line, I just have a Dirac point somewhere. So even though I can't define, like if I were able to find an insulator, I wouldn't be able to tell you what kind of insulator it was. But if I'm not, then at least I can tell you I have a topological semi-metal.
Oh, okay. So you mean this kind of magnetic Dirac semi-metals can be found by looking at the C3 representation? Yeah.
So like cadmium arsenide is an example with C4, or so with C3 like sodium bismuth or something. If you forgot inversion in that group, you wouldn't have symmetry indicators for insulators, but you still have symmetry indicators, from the co-rep multiplicities for semi-metals.
Oh, I see. Thank you very much.
Yeah, no problem.
Other questions, comments?
May I have another one?
Yeah, go for it.
Yeah, so I know you didn't calculate density function theory, but probably had heard something from those guys. So, well, the problem that I can imagine calculating topological materials could be the robustness of the density function theory, especially when we do with the magnetic systems. Do you hear anything about? Did you hear anything about?
Oh yeah, no, okay. So yeah, I mean, I wrote the, I helped with I edited the paper and did that. I wrote the editor, what's it called, the referee reports.
Okay.
And so so I went through all that, and so the idea is we did materials where somebody measured the magnetic structure, so we had a starting point. So we ran lots and lots of functionals and different Hubbard U's and things like that, and we made sure that we found at least one U or one functional where the magnetic moments match the experiment. And that at least gives some baseline that what you're doing is physically realistic in some limit.
So you
Without
started
that, you're flying blind, I think.
But are there many that still needs to be confirmed for the materials that I didn't take a look at the paper but
we did. I mean, we did the entire existing build-out database, but it's bigger. It's doubly big now.
Yeah, what portion of the database you think where you have a robustness in the DFT calculation of ledgers? I mean, I'm asking whether there is a room that I can get in.
Yeah, I mean, there's new ones, right? So what I would do is look at there have been updates since we last ran it. I am sure other people, that I know are also running these updates and doing calculations. But if they're labeled by date, you could look for a new one that was after our first archive posting.
Okay. All right, thanks.
But I mean, okay, so you have a better answer. Just look for stuff that isn't in it, like heterostructures and things. Like you can talk to experimentalists, and not everyone has uploaded their paper. And if you can work with someone where the magnetic space group isn't listed, they just know the ordering and figure out the magnetic space group, then that's a sort of more constructive from scratch approach to doing this sort of the right way.
I see. Well, I have another one actually. You mentioned the quantum spin liquid materials. Well, is it straightforward? I mean, it's not going to be straightforward. Is this possible that you can extend into the?
I mean, maybe. So my biggest issue is basically like, so we know from when we did like the eightfold semi-metal that you can't just like some quantum spin liquids. They look for things like frustration and triangular motifs and things like that. Right. And we know that that's just some hopping and some range of type binding model. And so when we did new fermions and that kind of stuff, that led to all sorts of spurious degeneracies and effects that melted away when you did higher range hopping or symmetry allowed terms. The right way was to have some symmetry and topology underpinning for what you could ever see in the spectrum. So this idea of going to the Kitaev limit or something like that doesn't match what we know from mean field theory. So I don't see why, if it's a harder system beyond mean field theory, that makes any sense. So at the very least, it'd be great to have some constraint where you could just look at a material and say something about the symmetries, the magnetic order,
Right.
and say that further constrains the kind of spin liquid you could have if you were to have one. So something like that. I mean, it's maybe it's nothing, but it's this kind of idea is like I would at least like to get the same level, something approximating the level of robustness that we have for these mean field materials for spin liquid prediction.
So you in progress? You're writing paper, or?
I mean, I'm just sort of like starting.
I see.
I mean, I have some ideas, but I'm talking to people about what is the best way, like these filling in force metals and stuff like that. So to see if you can do better now that you know all the magnetic symmetries. I mean, at the very least, you can map existing mean field spin liquids to quantum chemistry because it's mean field theory.
Right.
So the zeroth order question is, what do you get when you do the mapping? And I think that might be informative.
So have you had a chance to specify the symmetry representation for the Kitaev model? Well, it's the energy spectrum.
Not yet.
Okay, good. All right.
No, this is just starting. Like this is like this, this month. So.
I see. Right.
Yeah.
Thanks.
Yeah, no problem.
I also have 9 questions related to that. So in the spin liquid, after performing the symmetry group, I need to perform the gauge transformations too. And then does it make the story complicated or?
Yeah, I mean, the question becomes like, how do you treat all the components? Like, do they have different
Right.
groups? What are the constraints?
Which group you need to deal with?
Yeah, I mean, there's truly going to be some procedure that is less familiar than an electronic case. But at least at the very least, the group theory is done. And so you have the tools if you knew how to use them.
Right. I see. Any other questions, comments? If not, Ben, how long do you think you need to go through the bonus slide?
Like 5 minutes.
5 minutes? Okay, then I would like to, okay, so the formal session is over, but if you would like to listen to 5 minutes more about the new result, you can stay, the audience. So yeah, Ben, could you go to the bonus slide if you don't mind?
Sure.
Yeah.
Okay. So this is something that I worked on with Jungkook when I was a graduate student, and it shows up a little bit again in this paper. And so the idea is that in a lot of the low energy properties of topological insulators, crystalline insulators, and semi-metals can be understood from the perspective of Fermion doubling theorems. So the existence of compensating chiral charges in wild semi-metals comes from the Nielsen-Ninomiya theorem. And so there's sort of 2 classes in condensed matter physics of Fermion doubling manifestations. There's sort of unbeatable Fermion doubling theorems where you really have to break something like translation symmetry or charge conservation. And this is like because of the fact that the Broughton zone is periodic. So like if I have a plus Weil point, I can't go and you understand that a Weil point is like a descent relation in the Chern number. I can't go around the Broughton zone and get to a slice that I had before and disagree on the Chern number. So there must be a compensating chiral charge somewhere so that everything cancels out nicely. The same thing with a chiral mode, just I can't have a band structure that doesn't have spectral flow if I have some unpaired number of chiral modes. Like I literally can't write down the band structure in 1D. And then you have these cases where there's some sort of symmetry enhanced fermion doubling, where I have some additional rules, namely like tyrosal symmetry and how it's encoded, that affect the kinds of degeneracies I can see in my spectrum. And so for the sort of unbeatable ones and some of the symmetry enhanced ones, I can relate it to high energy anomalies. But as I mentioned earlier, we don't know all the anomalies because there's clearly topological crystalline insulators that have some other missing theory. So the best we can do is write down all the symmetry stabilized lattice models of topological semi-metals. And we know that it isn't in one of those lattice models, then it is not lattice regularizable. So the EBRs give you that. And so the simplest example, and this turns out to be related to a hierarchy of examples, is what you get in 1D with spinful time reversal. So in a 1D chain with spinful time reversal, no inversion, you can only have an even number of Dirac points. And this comes from either Cramer's theorem or some mirror symmetry and time reversal. So if I add more Dirac points, they come in pairs. If time reversal is, say, about the origin. You can circumvent this in two ways. The first way is with spectral flow. So the boundary of a 2D TI circumvents this form of fermion doubling, replacing an unpaired 2D Dirac cone on the boundary. And there's, if you think of it on a ribbon, there's a second Dirac cone on the other boundary. And so as a whole, the 2D sample has a sort of 1D lattice model if you make it very thick. But if you make it semi-infinite, it does circumvent this kind of fermion doubling. And the last kind turns out that if you make time reversal symmetry, in field theory, it's non-on-site or non-local. This very fancy field theory calculation. You could say, I wrote down a lattice model that that simulates the edge of a quantum spin Hall. But it turns out, if you look at the EBRs, this is just saying I have an anti-ferromagnet where time reversal squares to -1, it squares to +1. So I have a gap. I don't have a gap. I have the simplest anti-ferromagnet has at low energies the same theory as a 2D TI. So this hierarchy of fermion doubling, take the symmetry, get the restriction, place the object on the boundary of something with the symmetry encoded the same way as it is in the lower dimension, be in the same dimension in 1D, but change the way in which the symmetry is embedded, say make it non-local, is sort of a family of fermion doubling theorems that are established and then circumvented with magnetic exceptions or spectral flow. And so, Youngkook and I, and Charlie and Steve Young found a similar family with fourfold Dirac points in 2D. It turns out that because of quantum spin Hall or TCI phases, you have to have an even number of fourfold Dirac points with time reversal symmetry in 2D. You can circumvent that by placing the fourfold Dirac point on the boundary of a special TCI with time reversal and also some glide symmetries, or it turns out rotations and you slightly split it. And then Steve Young and I found that you can also do this exception where I have an unpaired fourfold Dirac point in 2D by having an anti-ferromagnet where I make time reversal act non-on-site, where I make the mirrors act non-on-site. And so what magnetic TQC lets you do is get all of the symmetry enhanced fermion doubling theorems. So for anything that doesn't have particle hole symmetry, you can look for all the combinations. So you can beat rotation anomalies and all sorts of other interesting stuff. And so this lets you figure out places to target for returning to high energy theory and trying again and looking at the symmetries to look for anomalies that you can measure in condensed matter experiments. And so this is one additional direction, a little bit different than DFT, in which you can use magnetic topological chemistry to look for interesting signatures of high energy topology.
So I guess that's it, or
yeah, that's it.
Okay. Yep.
Yeah.
Yeah. So thank you for the bonus slides. So if there are urgent questions you'd like to ask to Ben before finishing up the sessions, it's time. I have questions. So for these fermion doubling things, can they be avoided in the flow case system or non-equilibrium or non-Hermitian?
Yeah, but I want to caution by saying, in any system where you have other dimensions or rules like particle hole symmetry, you need to establish, and you don't know the anomaly. If you don't know the high energy anomaly, you have to establish the equivalent of EBRs in that group. And so it means you have to know the flow K space groups and the restrictions on the degeneracies in the flow K space groups. And if you don't establish all of them, like say it's superconductors, you might say you have an exception, but it turns out that there is some semi-metal that exists also in some superconductor flow K system that doesn't beat the rules as you've written them down.
Good.
So the key step is establishing the rules. Say here that time reversal is embedded locally, and then figuring out all possible lattice models that satisfy those rules. And that's where the sort of with extensions of the space group to flow case systems would come in.
Okay, I see. Yeah, thanks. Yeah, okay, then let's thank the speaker again for the nice talk and answering all the questions. And let's finish this talk. Yeah.
Okay.
Yeah, thank you. Ben,
Right.
yeah, you are always welcome to come by Korea and
Thank you.
my university.
When things are more normal, I will surely take you up on it because I am very sad not to be traveling right now.
Yeah. Yeah, you can drop by Youngkook and me, and I can give a tour for you in Seoul if you wish. So it doesn't need to be about physics. So when you come by East Asia, let me know. Yeah.
Yeah. Well,
and I'll be with you.
Well, let's aim for maybe this summer.
Yeah. Okay. So okay, that's all. And then I will. Yeah. So I think audience enjoyed the talk. So I will talk to you later.
Okay. Great. All right. Bye.
Bye.
Hey, Ben, but so since the official session is over, so
are you still recording?
Oh, I guess right. Yes.
Yeah, I want to stick around, but I will recording.
Well, I will email you. Well, I have a.
Yeah, just email me a Zoom link and we can chat.
Right.
Okay.
Good, great.
Yeah. Okay.
Or if you wish, I can cut out the video.
Well,
just email me a new link to.
Right, I'll talk to you later.
Okay.
Okay. Yeah.
Right.
Great to see you today.
Thank you for the nice talk, Dan.
Yeah.
All right.
Be safe.
Bye.